So good morning, everyone. Can we start the class? Okay. So if you notice on e-learning, I don't have the attendance today, so I will not be taking attendance today. I'm recording this this presentation or this our lecture today, and I will upload on e-learning hopefully by end of today. All right. So before I begin, I've announced on our WhatsApp group that we'll be having probably a test 2, right, by next week. And give me a minute, okay? So in the group, if you notice, I proposed test 2 to be on Friday, 22nd of January, 9 to 10 a.m. Okay, so by end of today, if you do not object, or if anyone doesn't object, so that is the date for our test 2. Okay, so the topics that will be covered for test 2 will be chapters 4 and 5. So chapter 4, we talked about robot arm kinematics. Right, in chapter 4, let me write it here. We talked about robot arm kinematics. So in robot arm kinematics, generally we talked about the forward kinematics, and inverse kinematics, right? So in forward kinematics, if you remember, it's all about, let me use another ink. In forward kinematics, so if you are given the joint angles, right, theta, and geometric link parameters, you should be able to derive or determine the pose, right? So what is pose? Pose is position and orientation. Position and orientation. So by the way, is my voice clear enough? Is it noisy? Do I need to use a different microphone or something? Can someone respond? Okay, good. So please interrupt me anytime if you have questions, okay? So once again, in forward kinematics, given theta 1, theta 2 up to theta n for a degree of freedom, we can compute pose, right? Pose is position and orientation. And in particular, we are interested in the pose of the end effector. And you know by now that we represent pose by homogeneous transformation matrix. Okay, and in this chapter as well, we talked about in this subtopic, right, in forward kinematics subtopic, we also talked about the Dinavid-Hartenberg representation, right? So this is a set of algorithm which will be given in your exam and so on, in your test. Representation. So this is an algorithm to determine the coordinate frames of every link or every joint in your robot arm. Okay, and we talked about the DH parameters, right? In particular, in DH parameters, we have theta I is always invariable. We don't assign a value for theta I. We have DI, AI, and alpha I. Okay. Of course, we learn some other things as well, so you have to refer to the notes. Okay, don't just rely on this notes. And then in inverse kinematics is the inverse of forward kinematics, more or less, right? So given the pose, position, and orientation of the n effector, we can compute theta. And in your syllabus, I've limited the computation to theta 1, theta 2, theta 3 only, right? And of course, in actual application, you have to compute all joint angles. Alright, so that was chapter 4. In chapter 5, we talked about the trajectory planning, right? What is it called? Chapter 5, planning of manipulator trajectories. So our Prime Minister is talking in the radio. Is anyone listening to him? So apparently there'll be an emergency declaration, right? Till August. So our COVID cases have been increasing quite dramatically. So they are imposing emergency state. And by the way, in Johor we have MCO, right? Movement Control Order from tomorrow onwards for the next 2 weeks. In case you haven't read the news. Okay, so in manipulator trajectories, we compute. There are many schemes, right? Types of trajectories, but we only cover 434 because the hope is if you know 434, of course you would know other schemes as well. So in 434, you learned how to compute the different segments, h1 of t, h2 of t, and h3 of t. So if you cannot remember, so h1 is the first segment of our trajectory, right? This will be a fourth order polynomial of fourth degree, and this is a third degree polynomial, and this is again a fourth order or degree of polynomial. And we have to compute in practical application, you have to compute h1, h2, h3 for every joint. Okay, so what happens in 434 trajectory is that you would have desired initial pose. Let's say I'm not going to draw the rest of the robot. Let's say this is the initial pose of n effector. Initial pose. And then you have a final pose of the n effector. Okay. So in 434 trajectory, we don't really care how the n effector moves, right? But all we care is in the beginning, if this is our initial pose of the n effector, after a certain time, we want the n effector to be in the final pose. How does it move in between? We don't really care. Because 434 is what we call the joint interpolated trajectory. interpolated trajectory scheme, because we'll be designing the trajectory of the individual joint without taking of the motion of the end effector. Of course, we do care the initial pose and the final pose of the end effector, but how does it behave in between these two, we don't care. And we only care about the motion of our individual joints. Okay, so I hope you realize that by now. So today, this is what will be covered in your test 2. Okay. Usually, the way I operate is your test will be exactly what we cover in class, right? Nothing extra. So if you understand our lectures, if you understand how to solve tutorial questions, you should be able to do test 2 very well. And it's only 1 hour. Okay. Oh, I have a question. Oh, clear, doctor. All right, sorry. All right, so today is chapter 6. So in your final exam, up to chapter 6 will be covered in your final exam. Okay, chapter 7, I don't think chapter 7 is in your final exam, but we will discuss again what will be assessed in your final exam when the time comes. Okay, so chapter 6 for sure it is in your final exam. So chapter 6 is manipulator trajectory. Let me try to make it bigger. Okay, a robot's end effector moves in Cartesian space. So you can imagine our 3-dimensional world is Cartesian space. Okay, we have x direction, x-axis, y-axis, and z-axis. So that is what we call Cartesian space. So when you operate your robot arm, the end effector moves in that space, right, with a translational and rotational velocity. And this is what we call a spatial velocity. So to get a better feel, what is translational velocity, what is rotational velocity, I have to draw. Unfortunately, I always have to save before I open new canvas, which I hate to do. Okay, now I just delete. All right. So this is your, let's say this is your robot arm. Okay, you have your robot arm. This is the base. You have your first joint here. Then you have the second joint, third joint, fourth joint, and let's say that's it, right? Then you have your end effector. Okay, so when the robot arm moves, moves about, if you only, for some reason, if you are able to focus on only the end effector, right? Let's focus only that end effector. If you keep your eyes only on the end effector, what you will be able to see is that the center of mass of the end effector, let's say this is the center of mass, right, of the end effector. First of all, you will see the center of mass moving around, right? You will see that it is probably moving in a certain direction. If you focus your eyes on this point, you will see it'll be moving. Okay, and if you focus on the whole end effector, you will see that it will rotate. It'll be rotating probably in x, y, z axis, right? So once again, if you have your robot arm, if you, let's say you use this robot arm to pick and place an object, if you fix your eyes on the end effector only, right, somehow, if you're able to do that, you will notice that the n effector will rotate. There will be a rotation in x-axis, y-axis, and probably in z-axis as well. And it also moves, right? Moves in a linear fashion. That means what it means is that if you focus again your view, your eyes on the center of mass of the n effector, that point is a point, right? The point will be moving in the three-dimensional space. So this is what we call the translational velocity. So this part right here, the fact that the point is moving is what we call translational velocity. And the fact that the n effector rotates in Cartesian space is what we call the rotational velocity. Rotational. Okay. All right. Let's get back to the notes. Right. So that combination of translational and rotational velocity is what we call a spatial velocity. Okay. So from now on, when I say spatial velocity, you have to know that I'm talking about the combination of translational and rotational velocity. All right. Just like your car, right? If you drive your car or motorcycle, when you move from one place to another, your car has translational velocity. It also has rotational velocity, right? Because if you have a drone taking the video of your car from the top, you will see that your car is rotating, okay? Because the heading of the car changes. All right. So, however, the velocity is a consequence of the velocities of the individual robot joints. Indeed, right? So this spatial velocity of the n effector is caused by the individual motion of the joints. Okay, remember in our 434 trajectory, we design the trajectory for individual joints, but the effect of that is your n effector moves from the initial pose to the final pose. Okay. So the three-dimensional n effector position and orientation has a rate of change which is represented by a 6 vector known as spatial velocity. So this I will explain again or in detail later. Why it is 6 vector? Because it's called a 6 vector. So this has 6 components. The combination of the spatial velocity, we will use the symbol nu. This is nu. Okay? It's a Greek symbol called nu. It doesn't matter, but this is the spatial velocity. Spatial velocity nu. It has 6 components. Vx, the x velocity, right? The y velocity, the z velocity, translational velocity. It has omega x. So this is the rate of rotation, or we call it angular velocity in x-axis. Omega y, omega z. See? So the motion or the velocity, the spatial velocity of the n effector has 6 components. 3 of translational velocity. This is translational. And this is rotational velocity. Okay. All right. So we are still on slide number 1. All right, so the joint rate of change and the end effector velocity are related by the manipulator Jacobian matrix, which is a function of manipulator configuration. So in this chapter, we will talk a lot about Jacobian matrix. So what is Jacobian matrix? Jacobian matrix will relate the joint velocity. So its joint, let's say this is theta 1, right? Theta 1 has its own, if you take the time derivative, it becomes theta 1 dot. So this is basically the rate of change of theta 1. It's like the angular velocity of theta 1. Okay? And similarly, theta 2 has that thing as well, right? Theta 2 dot and so on, right? Up to theta n. So what is the relation between the angular velocity of these joints and the spatial velocity? So that is what we'll be studying in this chapter, right? By means of the Jacobian matrix. All right. So in forward kinematics, like I've just explained in the beginning of this lecture, we discussed the relationship between joint coordinates and end effector pose. Right? In forward kinematics, if I give you the joint angle, you can compute the homogeneous transformation matrix that represents the end effector's pose. And now we investigate the relationship between rate of change of these quantities, between the joint velocity or the angular velocity of the joints and velocity of the end effector, the spatial velocity. So this is called the velocity or differential kinematics of the manipulator. So let's illustrate the basics with a two-dimensional example. So this is a two-link robot. So you can imagine this robot only operates on the XY plane. Okay, so it has the length of link number 1 is A1, the length of link number 2 is A2. We have the angle. Later I will call this theta 1 and theta 2. Okay, so this is the angle from x-axis of link number 1, theta 1. This is the angle of link number 2 from this axis, right? From link number 1's axis. This is what we call the theta 2. And we don't have an end effector, but let's assume this point represents our end effector. And the position of this end effector is called xy. So nu is the velocity, dp dt. So the time derivative of the point p. So you get only translational velocity. Okay. So dp dt is translational velocity. So the position of the end effector is given by this, right? You can easily derive this, right? Can you think? Yeah? You can. Sure. Okay, good. If you can. Who's texting me? All right. Okay, let me show you anyway. All right, in case if some people don't know. So I hope you will not ask me about this again. Okay. Well, you can. Okay. Well, we want to know what is this one, what is this point, right? So this point is, of course, this point has two components, x component and y component, right? So this is, let's call this, if you can call this py if you want, and this part right here you can call it px. Okay, so px is this length right here, right? This length, it should be a straight line, this length plus this length. Okay, so this is what? This is a1 of cos theta 1. Remember, I call this theta 1. Okay, this is theta 1, this is theta 2. Right, this is a1 cos theta, and this length right here, this is a1 sine theta 1. So I'm just going to use a simplified notation, right? So similarly, you can compute for this part over here. So this should be what? A2 sine of this angle, right? This whole angle. So this angle is theta 1 plus theta 2. Okay, so that's how we get the first element here, a2. Sorry, it has to be cos, right? It's not sine. How do I erase? Brush library? Nope. Brush palette, right? So this looks like an eraser. Yes. So this is cos. So the first element a2 cos theta 1 plus theta 2 plus a1 cos theta 1. All right. So similarly, you can derive for the second element of py as well. All right. So let's compute a matrix that we call j theta. So j of theta is this one. We take a derivative over theta. All right. But what is theta? Theta is a vector, right? It has two elements, theta 1 and theta 2. Okay, theta 1 and theta 2. So how do you take derivative or perform derivative of a vector with respect to a vector? So you might not have seen this before. Okay, so the way we do it is d px, right? The first element, right? Remember, I call this px. This is py. So dpx d theta 1 dpx, we take a derivative with respect to theta 2. Well, it should be partial derivative, right? But never mind, you know how it works. Let me just correct it. Mathematically, it should be so this is px dy. So mathematically, we will write this as partial derivative dpx del d theta 1 Okay. So we take a partial derivative. So the first row, we take partial derivative of px, right? But the first column with respect to theta 1, second column with respect to theta 2. In the second row, we take partial derivative of py. The first column is with respect to theta 1 and the second column with respect to theta 2. Okay. So what is let me write it here. What is del px with del theta 1? So we take the first one, the first element here, we perform derivative with respect to theta 1. So when you perform, A2 is a constant because A2 is the length of the link, right? So A2 remains. When you take derivative of cos, it becomes minus sine, right? Minus sine. Whatever is inside remains. And if you do partial derivative of theta 1 and theta 2 with respect to theta 1, you just get 1. Okay, so we can, you don't have to write 1. So we take, because it's a summation, the derivative is also summation. But so A1 remains as A1, cos becomes minus sine. Theta 1 remains inside. So the partial derivative of theta 1 with respect to theta 1 is 1. Okay, so you have minus A2 sine theta 1 plus theta 2 minus A1 sine theta 1. Okay. Next, let's take partial derivative of del px with respect to del theta 2. So again, we have to refer to the first element, right? So A2 remains, it's a constant. Because in here we have theta 2, so we can't perform derivative. Cos becomes minus sine. And it's the arguments remain as theta 1 plus theta 2. If you take partial derivative of theta 1 plus theta 2 with respect to theta 2, you get 1. Okay. Next, we have to perform derivative of this with respect to theta 2. But it does not have theta 2, therefore it's 0. Okay. So you have del px over del theta 2 equals minus A2 sine of theta 1 plus theta 2. Alright. So do you have any question at this point? Okay. Similarly, we can do the same for del py del theta 1 and del py del theta 2. So do I have to show you del py del theta 1 and del py del theta 2? Yes, sir. Nur Hayati Sarir said yes. So we have to respect that. No problem. Okay, let's see, right? What is py? This is py, right? This whole thing is py. So we want to compute this part right here. So del py del theta 1. So we take this, we perform derivative with respect to theta 1 plus this term, perform derivative with respect to theta 1. So A2 is a constant, so it remains as A2, right? If you take derivative of sine with respect to the thing inside here, it becomes cos. And the arguments remain as theta 1 plus theta 2. And according to the chain rule, if you remember your, I don't know, first year mathematics, or was it second year? I don't know. Next, you have to perform derivative of this argument with respect to theta 1. And the answer is 1. Okay? Plus derivative of this with respect to theta 1. A1 sine becomes cos, which is theta 1. Okay? Good. Next, let's perform del py del theta 2. This one right here, right now. Okay. So similarly, we have a2 because it's constant. Sine becomes cos. Whatever inside remains as it is. If we take, and again, according to the chain rule, taking a partial derivative of theta 1 plus theta 2 with respect to theta 2 is 1. Okay, now plus, so now we have to perform derivative of this with respect to theta 2. It does not contain theta 2, so therefore it becomes 0. Okay, so we have computed the J matrix. It's called Jacobian matrix. And for this example, it's very simplified, right? We only consider translational motion. So this is the matrix, you see. It's a 2 by 2 matrix. Let's go to the notes. What does it say? Okay, so we have this matrix. What's next? Look at this, right? This is J is dp over d theta. So if we bring this to the right, we have dp equals to j of theta multiply d theta, like this. And then we can divide on both sides with dt. Okay. We have dp dt equals to j theta d theta over dt. And what is dp d theta? It is p dot, right? It's a time derivative of p, which means it is the velocity of this point, the translational velocity of this point. So we have p dot equals to j theta, j of theta, theta dot. And the Jacobian matrix, the j of theta, right? It maps velocity from joint coordinate or configuration space to the end-effector's Cartesian coordinate space, and itself a function of joint coordinates. So first of all, let's define or describe one by one. It says is itself a function of joint coordinates. So j of theta, right? So the matrix itself is a function of joint angle. Look at this, right? For different values of theta 1 and theta 2, you would have a different matrix. So that's what we mean by J is a function of joint angle or joint coordinate, right? Because it depends on the values of theta 1 and theta 2. Okay, and from this equation you can see J maps from joint coordinate or joint angular velocity to the configuration space or the end effector's velocity. So if you know the angular velocity of every joint, then you can know the velocity of the end effector, right? So this is an example. So the configuration of a two-link robot, the same robot as we saw earlier, right? But now it is simulated in MATLAB. With theta 1 equals to 0 and theta 2 equals to 0 is shown in figure 2. So this is figure. Theta 1 is 0, theta 2 is 0. And this is the Jacobian matrix, right? So let's try to substitute theta 1 0, theta 2 0. What do we get? So if I have let's say theta is 0, 0, right? So what happens to j theta? Sine of 0 is 0. Again, sine of 0 is 0. So the first element is 0. Here, sine of 0 is 0. And here, cos of 0 is 1. Right? And so it becomes a2 plus a1, because here again cos of 0, right? And how about here? We have a2. Okay. So if a1 equals to 1 and a2 equals to 1, what will be our Jacobian matrix? It will be 0, 0, 2, 1. Right? Okay. So in this configuration, theta, where theta 1 is 0, theta 2 is 0, the motion of joint 1, the first column, causes motion in the world y direction. Okay, why? Can you please explain? Can someone explain to me why it says the motion of joint 1, the first column? Why that's the case? Can someone explain, please? What? Say it again. Because it consists of, it says motion of joint 1, the first column. What does it mean? Nur Hayati, are you there? Please don't tell me you don't have microphone. Oh, you're thinking, okay. Okay, good. Let me just explain, okay? Maybe it's too new. But Tafarel, thanks for your answer. I did not hear you correctly. Maybe you answered correctly, but let me try to explain, all right? Oh, I hate this. Now I need to open a new file, but then this thing will be lost. Okay, I'll try to write it here, okay? Please bear with me.